I'll just. So, hi everyone, I'm Shay, and today I'm going to talk about the binary search. And binary search is basically an algorithm like searching for a specific element from a sorted array. And notice that this array has to be sorted, either ascending or descending, but it has to be sorted in order for us to apply the binary search. So let me adjust this for a second. Okay. So in today's example, we have an array of 8 elements, and each element have a corresponding index. So for example, the first number has a corresponding index 0. So you can just remember like the index always starts from 0 in Java. And the last index is 7, but we have 8 elements here. So you can notice that the last index in an array is always the length of the array minus 1. In this case, is 8 minus 1 equals 7. And we're going to search for 2 test numbers from this array. The first one is 32, which does exist in this array, and it is at index 6. And the second test number is -3, which does not exist in this array. So we will see what happens. And so the first step we're going to do is to identify the low, mid, and high position in this array. So obviously, the low position would be at index 0, and the high position would be at the last index in this array. And we can use our formula here to calculate the mid position, which is 0 plus 7 divided by 2, which is 3.5, but we'll just use 3 here. So this is our mid position. So the next step is to ask yourself if our test number equals the number at the mid position, like if 32 equals 19, and the answer is no. So we're going to ask ourselves again, like if 32 is smaller or larger than 19. So because 32 is larger than 19, then we can narrow the range of this array to here. Because this array is in an ascending order, and 32 is larger than 19. So it must be on the right side of 19. Then we can narrow our range to this. So we're going to do the same thing, because now we have a new array. Then we're going to re-identify our low, mid, and high position. So our low position would change from index 0 to be at index 4, because this is our new array. And obviously the high position would remain to be at index 7, because this is our array, right? And we're going to calculate the mid position again, which is 4 plus 7 divided by 2, which is 11 divided by 2, it's 5. So our new mid position would be at index 5. Yeah, and then we just do the same thing. We ask ourselves if 32 equals 29, and the answer is no. So because 32 is larger than the number at mid position, 29, so we can narrow our range again. So this time our array would be just this part of the original array, because 32 is larger than 29. So the new array must be on the right side of 29. So now we change our low, mid, and high position again. So our low position would now be changed from index 4 to index 6. And our high position would remain to be at index 7. And we're going to use this formula to calculate the mid position again. The mid position would be 6 plus 7 divided by 2, which is 6. So this is our new mid position. And now we're going to ask ourselves if the test number 32 equals the number at mid position 32. And this time the answer is yes. So in the first example, we have successfully found our test number, and it is at index 6. The second example is to search for -3, which is a number that does not exist in this array. But I'll show you the how it works by using binary search. So this is our original array. Like we have the low position to be at index 0 and high position to be at index 7, and our mid position to be at index 3. And this time we're going to search for -3. And so we ask ourselves if -3 is equal to 19, and the answer is no. So this time we have to narrow our range to here, because again, this is an array in ascending order. So if -3 is smaller than 19, then it must be on the left side of 19, and so we get this new array here. And so now we can move our high position from index 7 to index 2, because this is our new array. And we should calculate the mid position again. We should get a new mid position for this part of the array. So mid would be 0 plus 2 divided by 2, which is 1. So the number at index 1 would be in our new mid position. And we ask ourselves again, if -3 equals -2, and the answer is no. And because -3 is smaller than -2, then it must be on the left side of -2. So this will just be our new array. And we can move our high position from index 2 to index 0. So this becomes our new high position. And we should calculate the mid position again. The mid position would be 0 plus 0 divided by 2, which is 0. So this is our new mid position. And we ask ourselves if -3 equals -7, and the answer is no. But -3 is obviously larger than -7, so it should be on the right side of -7. So we're going to move our low position from index 0 to index 1. And now you may notice something that is really weird, because we have an array in ascending order, but now we have our low position to be on the right side of high position, and that's not correct, because low should always be on the left side of high. So if you encounter this case, it just means that this number does not exist in this array, and you can just stop searching for this number. Yeah, so that's how binary search works. And then I can show you how it looks like in the code. So I have two classes here. The first one is binary search class, and the second one is binary search test class. So the algorithm of binary search is in the binary search class, and we're going to use the test class to test if this method works successfully and correctly. So in this binary search class, I first define and initialize the not found position to be equal to -1. And this means if we don't find our test number at the end, the output will just be -1. That means you will just get -1 as your output. And here is the algorithm of binary search. So in this binary search method, we're going to pass in an array and a test number. And so first we define our found position to be not found. That means we assume that we haven't found that test number at the very beginning. But if we found that test number, we can change the found position from not found to be the number at index mid. Do you remember, like we always found our test number at the mid position? So if you ended up to like successfully found that test number, you can change the found position variable from not found to the index at mid position. And here are the same thing. It's exactly the same thing I just talked about. Like we define our low position to be at index 0 and the high position to be at the last index, which is the length of the array -1. Like if you have 8 elements, then the last index would be 8 - 1, and it equals 7. And we define our mid position here. So here's the while loop. In this while loop, only if the conditions in this parenthesis is true, we're going to execute the rest of the loop. So the condition here means if our found position variable equals not found, which means only if we haven't found that position. And this symbol here means end. And only if the low is on the left side of high, if this is an ascending, an array in ascending order. So only if we satisfy these two conditions, we're going to execute the rest of the loop. So this is the formula we used just now, and we use it to find the mid position. And in the example we just did, we always ask ourselves, like, if the number at mid position equals the test number. And if it is equal to the test number, then we will change our found position variable from not found to the index at mid position. And if we successfully found that test number to be at the mid position, we will just return that found position, which is the index at mid position. And so if we don't find that test number at the very first, we will ask ourselves if the test number is smaller than, if it is greater or smaller than the number at mid position. And if it is larger than the mid position, then we will like narrow our range to be like, we change our low position to be at mid +1, because the test number is clearly on the right side of the number at mid position. And the else here means if the test number is smaller than the number at mid position, we're going to change our high position to be mid -1. And that's exactly something we did when searching for -3. So like if we got the test number to be smaller than the number at mid position, the test number must be on the left side of the number at mid position. So we will move our high to be at mid -1. And we would just continue looping until we find, until we change the found position from not found to mid. And then we can return our found position. And, or like there might be another situation, like if the low is no longer smaller or equal to high, like when we search for a number -3, if the low is on the right side of high in an array in ascending order, then we can tell that this number just does not exist in this array. Then we just don't need to execute the rest part of the loop. So yeah, that's how binary search works. That's the basic algorithm. So then I'm going to find, test this method of the binary search test class. So in this test class, I created a sorted array, and there were 20 elements in this array. And this array have numbers from 5 to 100 by 5 in ascending order. So for example, you have I equal to 0, then 0 plus 1 equals 1, 1 times 5 equals 5. So the array would start from number 5, and then like 5, 10, 15, 20, 25 until 100. And here, these are just the things I'm going to print out in the output. You can just like type everything you want to like see in our output here. So so in this array, we're going to search for 5, 100, 35, and 68. So I just mentioned that this array only contains numbers like from 5 to 100 by 5. So that means 5, 100, and 35 exist in that array, but 68 does not. So we're going to call the binary search method from that binary search class to apply the binary search to help us search for number 5, 100, 35, and 68. And you may also notice that here's a pet left method and a string character and comma 3, and that's just the format of pet left method. It just helps you to make the output looks nicer. But that's not our focus today. So if you have any question, you can ask me later. So yeah, this is just the pet left method. So I'm gonna like run this class and see if the binary search algorithm works successfully. So here's our output. Like we have this sorted array from 5 to 100 by 5, and these are the numbers we are going to search for, and these are the index of these test number. So our number 5 is at index 0, and number 100 is at index 19. So that means our binary search algorithm works successfully. And for number 68, it returns -1 because we have initialized the not found variable to be -1. So of course we can't find this number in the array. So the found position will remain to be not found, even after like the loop. So our output would just be -1. And yeah, that's our output. So yeah, I've finished presenting the code, and then the final step is to talk about the time complexity. And so like, for example, if we have 8 values in an array, like there were 8 numbers, sorry, and we're going to do 3 comparisons, because we have calculated the mid position for 3 times. Like first, we calculate our mid position to be at index 3, and then something like at index 5, and then it's at index 6. So we have done like 3 times of calculations, like 3 comparisons. So in the same way, if we have 16 values, we're going to do 4 comparisons. And if we have 32, then 5, 64, then 6 comparisons. So here's the conclusion. Like if we have 2 to the power of n values, then we're going to do n times of comparisons. So for example, 8 equals 2 to the power of 3. So that means n equals 3. So we're going to do 3 comparisons. And the next line here just means, it's just the other way of expressing the first line. That's an algebraic thing. So yeah, so that's, this is the time complexity for binary search. And this is the graph of order n versus order of binary search. So order n means if we have 8 elements, then we're going to do 8 comparisons. That means if we have n elements, we're going to do n times of comparisons. But for binary search, if we have n values, we're just going to do log to the base of 2 n times of comparisons. And the blue line represents order n, and the yellow line here represents the time complexity for binary search. And so you can see that the binary search uses much less comparisons than the order n, which is the linear search. So because we're cutting our array like from half to half to half, so that really saves a lot of time, and you don't need to do that much of comparisons for binary search. Yeah, and yeah, that's and here are some helpful links. This one is the binary search algorithm in different programming languages. So if you also want to know the algorithm in like Python or C, you can have a look at this article. And this is a video talking about binary search. And this link shows some practice problems which help you to apply the binary search to some real life examples. Yeah, and so I guess I talked a little bit fast today. This is the agenda for the following weeks. And yeah, thanks for coming. And do you have any questions? Because this is the end of the presentation.